Okay. Hello, everyone. This week is week 7 of our IEEE symposium on data analytics and Internet of Things. Today we have a special guest, Dr. Aravinda Rao from University of Melbourne. Before introducing Dr. Aravinda, I would like to also mention that we have another week to go with this IEEE symposium. And also we have 2 more talks this week. Les Davy is going to talk tomorrow. And also Len will talk on Thursday. And next week we have talks from Massachusetts Institute of Technology, Amazon, and one more talk on, and also panel discussion will be on next Thursday with the awards for poster competitions. So I would like to introduce Dr. Aravinda Rao. Dr. Aravinda is a research fellow at the University of Melbourne. He's also coordinator of Internet of Things sensors, and his research areas are in Internet of Things, computer vision, and machine learning. He has developed and designed many intelligence IoT systems and algorithms for real-time applications such as smart city applications and noise monitoring and water quality management. Please join me to welcome Dr. Aravinda for his talk on artificial intelligence in big data analytics and Internet of Things applications.
Thanks, Satar. Thanks for your kind introduction. So I am working as a research fellow in the Department of Electrical and Electronic Engineering, University of Melbourne. I am within the group called ISNIP within the department. It stands for Intelligent Sensor Networks and Information Processing. So our group basically, we work on developing AI algorithms and also big data analytics with mostly linked to Internet of Things applications. So in this talk, I will go through some 5 case studies that we did through in our group. I think it highlights some of the challenges that we encounter when we are applying artificial intelligence and analytics for IoT applications. So if we look at the number of devices, IoT devices that we have currently, it's about 26 billion devices, mainly using IoT technology worldwide. So this was only about 15 billion in 2015. And it is projected to increase by around 3 times to reach 75 billion devices by 2025. That is a huge number. And the amount of data that would produce from these devices will be enormous. So currently, like in 2018, the number of IoT devices that they were producing the data, it was around 2.5 into 10 raised to 18 bytes. That is 2.5 quintillion bytes of data every day. And what happens with these devices when we connect more devices to the internet is that they produce a lot of data, and it becomes a challenge to acquire, store, process, and visualize all this data, and also finally to interpret what this data means. Like, how do we use this data for our use cases or the scenarios that we are interested in? So basically, all these constitutes what is called the big data. They are characterized by 7 V's: volume, velocity, variety, validity, variability, visualization, and value. So if you look at the data volume from IoT devices in 2019, there were around 13.6 zettabytes. So just to give an information, 1 zettabyte is equal to 10 raised to 21 bytes. That is a lot of data that was produced in 2019. So if you compare that to the projected 2025 volume, it would be around 79.4 zettabytes. There's a lot of data to process, store, and even to make some meaningful sense out of the data. So the previous statistics basically tells the data that was generated from IoT devices. If you consider other devices that are not connected to the internet but in different forms, if you consider all the devices that are generating the data, mainly digital, then it is projected to be around 149 zettabytes by 2024. So this accordingly, what is happening is the artificial intelligence market is also increasing in terms of market size. If you see by 2025, we will have the market size will be around 125 billion US dollars. Similarly, currently it is a $25 billion. So it is almost going to be increased by 3 times by 2025. So there is what all these graphs indicate is that there is going to be a need for artificial intelligence, very high demand in the next couple of decades, as well as the few years coming. And we have so many devices connected to the internet, and how to make the sense from the data and how we can create some innovations around the data, and also how we can improve our existing engineering systems using artificial intelligence. So what are some of the main drivers that are causing this increase in data, IoT, and artificial intelligence? Mainly are the low-cost sensors. Earlier, a few decades ago, sensors were very, very expensive, but now we have sensors that are very cheap and easily manufactured. And also the advancements in memory, basically following the law that used to nearly double every 2 years. And also the computational power, we have now more CPU processing units, and also graphics processing unit, and data centers, edge technology. A lot of computation power is available to almost everyone now. And also the communication aspect. Earlier, we didn't have sufficient communication technologies to connect one device to another, or to connect all devices to the internet, or to make up the network that connects devices to one another and talk to one another. But now with the wireless communication, everything almost, it seems very easy to connect and communicate and transfer data from one point of the network to another. Similarly, all these reasons are leading to more availability of data, as well as people are more willing to contribute to the data, whatever they have created in their own labs or institutes, or through their mobile phones, or through the other different devices. So some of the challenges that arise from all this data is understanding what the data is, what the data is critically telling about, and ensuring the reliability of the data. Because many times what happens is you have the data, but you don't know whether it is good enough. So you need mechanisms to ensure that the data is, whatever you have collected is correct, and you can use the data to make inferences for future usage. Also, validating the data. You would also need experts to ensure that the data collected is in line with the scientific process or the recommended guidelines, and the data conforms to the rigorous standards. The second challenge is developing robust models. Robust, I mean here, you can, using the data, you can create a model using some artificial intelligence technique, like an algorithm. But many times what happens is it is too specific. Say, for example, you create a algorithm which works on the data that you have, but if you give any other data, it doesn't give the same performance. Basically, what it tells us is that the model is not generalized, in the sense it's not robust enough. If you change the data to different environments or different contexts. Also, it doesn't mean that you have to totally put a different data, but it is when you have similar data, but it doesn't give the same performance, that means it is not general enough for related problems or a very similar problem with slightly modified data. The third one is when you have this data, correct data, when you have the robust model, now the question comes how you integrate everything into your existing system, because we cannot throw out our existing system completely. So we have to ensure that whatever we develop is adaptable to our existing system. So that is what is called a system of systems approach for effective implementations. And the final challenge is it's a bit difficult to derive the critical knowledge and reasoning behind some of the models, and how everything can be made sure that it is kind of efficient. Sometimes it may appear sufficient when we put in together, but after some days or some years, it may not work as we expected, because most likely it could be that there was a lack of knowledge and reasoning behind this approach. So it is very important when, for example, in systems where we use in healthcare, so we need logical reasoning and critical techniques, scientific techniques to analyze and reason out why the system is working. We cannot blindly say that the model gives good results, so we can use it. So that is one of the important things as well. So as mentioned earlier, so I'll be discussing these 5 case studies. The first one is the real-time urban forest monitoring that we did it in Melbourne, and the second one is how to impute missing data from the same case study. And the third one is how we can use artificial intelligence in real-time crowd monitoring that we did with one of the projects through ARC linkage project at Melbourne Cricket Ground. And also the fourth one, I will discuss about how artificial intelligence, especially deep learning, can be used for real-time crack detection. And lastly, I will discuss on how we can use AI for monitoring stroke patients. So in the first case study, this is about real-time urban forest monitoring. This is, if you look at this figure, this is, we have a figure which shows the temperature as a heat map. There is one point here, it is saying 38.3 degrees Celsius, and the other one is 80.7 degrees Celsius. This 38.3 degrees Celsius is the actual recorded temperature under the tree. And this one is on the road, on the concrete surface. And what it shows is, this is in the CBD. What it shows is that even during daytimes, the temperature can go as high as 80 degrees on the surface. And this is very important to understand, because many times there will be pedestrians who are vulnerable to high temperatures and who may be affected because of these high temperatures. So one way, so the question is, how can we tackle this? This effect, this is related to something called urban heat island effect. What it means is, urban heat island effect simply means that because in today's generation, we are building more concrete structures, we observe that usually the center of the city absorbs more heat from the environment during daytime, and it releases slowly compared to the coolness that we can see in the outer suburbs. In the sense, so the center of the cities will be more heated, and they take longer time to release the heat because there is a lot of concrete structures in the CBD. So essentially what it means is that we need some mechanism to lower this temperature. And one way to do is by having a lot of trees in and around the cities. So this is a screenshot of urban forest visual from the city of Melbourne. So they have got around 70,000 trees, and they are maintaining the trees, and they replace the trees that are old, and they monitor each tree regularly. So because of the heat and water restriction, it is expected that around 27% of the trees we may lose in a decade or so. So what we did was we deployed sensor networks through 4G technology to send the data from the field. So we deployed a set of 5 sensors at Fitzroy Gardens in Melbourne, and also a set of 4 sensors at Docklands Library. So each sensor with the temperature, humidity, and light. They had with these 3 sensors, each sensor node used to send data to a central database. Here in the yellow mark is the receiver that receives data from all the other nodes. And similarly at Docklands Library. So we used to collect this data at an interval of 10 minutes. We collected this data for around 8 or 9 months. And the objective here was to see whether having a tree canopy cover, that means if there is a good canopy cover from the tree, whether it will affect the temperature or not. So this is how the setup is. So we had also solar panels connected to the sensor so that they can run 24 hours. And we collect the data using Zigbee wireless communication through a base station called Meshlium. And we use 4G to send it to a cloud. And then we do spatial temporal estimation, anomaly detection, and visualization. So one of the challenges here is that when we have these inexpensive sensors, we don't know whether the readings are good enough, in the sense they provide a good reading, but we still are not knowing how good the sensors are giving the readings. And also because one of the main reasons for using low cost sensor is that we cannot use very high precision expensive sensors all the places. So then the alternative approach is to use high precision sensors at sparse locations, very few locations, and along with them we can use a couple of low cost, low precision sensors. Then the problem issue is that how to ensure that the low precision sensors give very similar readings as high precision sensors. So in order to do that, we need to estimate data at unknown sensor locations, as well as compensate for any errors. So here we see that the top one is the Fitzroy Gardens deployment, and the bottom one is the spatial estimate using a technique called Bayesian Maximum Entropy, where we interpolate what could be the likely temperatures at places where we don't have the sensor nodes. And similarly, on the right-hand side, we see a similar one for the Docklands Library. So this Bayesian maximum entropy, it gives a very good temperature reading, as well as light and humidity for different intervals. So we analyzed this information, and we were happy that it gives a reasonably good estimate of a high precision sensor if you were to use high precision sensors alone. So other problem that we faced was that sometimes there used to be a sensor which was giving always negative reading, or sometimes the values were very low. So the ones that are marked in this red color here is actually that was giving anomalous readings. So we use something called hyperellipsoidal clustering to detect these anomalies and identify those data packets and compensate using distributed anomaly technique. I'll move on to the next one. So the second one is related to the first. The second case study is related to the first case study. So in this case, we try to impute the missing data. So in the first case, we saw that basically how to estimate sensor readings at unknown locations, as well as how to detect anomalies. In this one, how to estimate the data if there is if the data is missing. The missing data could be because of error in communication, or the packet is lost in communication, or there is some problem when the data was sent and there was some error in encoding or decoding scheme, or it may be that the sensor has permanently failed. So again here, using Bayesian maximum technique, what we do is we take the raw data from the sensors and we create an experimental variogram. Variogram is like a function that tries to map the spatial estimate from different sensors to say from one point to another point how likely the estimate would be. So there are three steps, basically: the prior step, meta prior step, and posterior step. In the prior step, we use the mean and covariance functions from the sensor readings as an input that is given to as a general knowledge to the entropy maximization step, and then we get prior PDF probability density function. So in the meta prior step, it is more about specific knowledge that we know about the problem. So basically here, we give about how frequently the sensor reading is given and any specific type of sensor reading that we are interested in. In the posterior step, we combine information from prior PDF and as well as specific knowledge to get posterior probability density function, which will result in a spatiotemporal map. So here, this is an example, and we have a comparison here. So we are comparing Bayesian maximum entropy with probabilistic matrix factorization. This is PMF is one of the most widely used interpolating scheme for missing values. So we have compared with that, and we found that in terms of percentage of missing values, our approach, which these two are our approach, where we are giving results for hard and soft sensor data. Hard data means actually the high precision sensor, and soft data is for sensors that we may obtain because of uncertainty or some low precision sensors. So our approach consistently gives reduced root mean square error for both hard and soft cases. Similarly, in terms of the time it takes to run to execute the program and get the results, we see that our approach is consistently lower, whereas the PMF, initially it decreases for a missing value. It is increased for missing value, and slowly it decreases in time as more missing values are given. So one of the advantages of our approach is that it is robust to variation, and also it is very good if you are to use on IoT systems, and also it makes it very suitable for distributed decision making if we deploy it on the sensor nodes, IoT nodes. So next, moving on to the third case study. This is about crowd monitoring at MCG. So just to give a context, around 70% of the world's population, so it is expected to live in cities. So this naturally results in people traveling more often, and so traffic congestion, congested roads, overcrowded public transport, and also demand for more energy, and also likely public safety. As more people will congregate, they will go out for music events or some other sporting events, etc. So these are some of the like typical applications where we might likely use video surveillance, like somebody is climbing a fence and entering into a building. And there is also intrusion detection, where you are not supposed to enter some places, restricted places, but still you're trying to enter. And people may be loitering around a certain place, monitoring some activities. Then you can detect whether that person is constantly in the same place looking for something. And also they may leave some objects that likely to be dangerous. And also people in some places jumping the turnstile to get into a public transport or some other places. So in all these cases, we would want our systems to detect such activities. So similarly, at MCG, it has got around 350 cameras, IP, that is internet internet-enabled cameras. So it has got around, it has a capacity of 100,000 people it can host. And so the challenge here is, for example, if there is an event such as a fire, and you would want to evacuate people from the stadium quickly, but in a safe way. But you would not know how many people are there in different parts of the stadium. So it will be a very monumental task if you start counting how many people are there, how many people are seated, how many are standing, how many are in the corridor, how many are walking in the ramp. So there are different places that people could be, and if you want to evacuate them quickly, you would need a good way to analyze the situation and evacuate responsibly. So for that, we believe that video analytics could really help. So in this case, we developed analytics to count how many people are there in different areas. And also, like, it can help in understanding the relationship between people, what kind of behavior they have, whether they are loitering around, whether they are waiting for someone, whether somebody has fallen somewhere on the corridor. So all different scenarios and events can be captured through video analytics. Otherwise, it will be a huge task to count manually and talk to one another and coordinate and then evacuate. So this shows an example case where we have deployed 6 cameras in different directions facing ramps and stairs and corridors. So this is how the pictures inside from those cameras look like. So there are people at different places walking. If you look at this, you could imagine like how many people are there, how do you count each one, and that to objectively, in the sense, many times you may make mistake thinking the person is there, and but the person may not be there. And also there will be many people who are walking together and you may miscount them. So it is a very challenging task even for video analytics, like artificial intelligence, to identify individual person and count them. And it has to be fairly real time, because you don't have enough time to process this and give the result. It has to be in real time. So we have developed few techniques to count people where, for example, here there is a line. It is an imaginary line that we have drawn. So whenever people cross this line, the counter increases how many have gone, and it gives an indication of total number of people as well as the current number of people moving. Similarly, here we can track people. It can give individual IDs for each object, each person, and we can make sure that the person who has been here is also seen as the same person in a different camera. So that is called tracking across multiple cameras. And density estimation, this is where This camera is fixed at a very high position, so the people, the height of the people that you see from the camera is very small. Because of that, you see the people as a very tiny object. So in these cases, estimating, counting people is not feasible. So what we do is estimate the density, how many people are there in roughly in a square meter area or so. The other application is suspicious behavior detection. So we can detect how many people, if any people is loitering around talking on a phone, and he's waiting for someone or something to happen, we can automatically detect through video analytics. So this is just a video that shows how crowd events, such as when people are moving together, when they split, it indicates through an arrow they are splitting in different directions. Next, the case study 4, I will talk about real-time crack detection. So traditionally, so we have these buildings and there are cracks. It happens because of aging, as well as different factors associated. Using wireless sensor networks, you can attach the sensors to the wall that measures if there is a crack, because it can stick, and if it expands, it says that yes, there is a crack. Similarly, when you have a lot of vehicles moving on the bridge, eventually you will have some of the cracks appearing on these pillars, as well as the concrete structures associated with the bridges. So when you have bridges like this, it is sometimes very inaccessible to reach to the places and monitor whether there is a crack. And also in these buildings, sometimes it may not be visible unless you go near the site location. So using wireless sensor networks plus IoT, you can detect back, report, and monitor all the status of the cracks in real using these sensor networks. This gives a local view of what is happening here. Similarly, if you integrate all this from the buildings, from the bridges, everywhere, everything, then you'll get a global view of overall whatever the location that you are interested in. It will give a good idea of what is happening everywhere. So the other approach, this is one way of doing it. The other approach is using visual inspection, that is using cameras and drones. Using cameras, you can take the video of the buildings or the bridges or any other structures that you are interested, and then you can use deep learning to analyze the images whether there are cracks. One of the advantages of using cameras is that you also get 2D and 3D structures of the 2D and 3D structural information, not only about the cracks that you would obtain using sensor networks. So that advantage has huge implications when you are trying to build a smart city wherein you want to integrate different buildings, different structures in a sound and good way, such that the critical infrastructure of the nation is protected. And also many times people will be traveling and there's a lot of traffic and all these things. So you want to know what is happening in real time, and also whether the structural integrity is maintained, not only in terms of where the crack is, but how it may affect other structures. So for that, combining both wireless sensor network information as well as camera data is very helpful. So I think I briefly explained this. So for example, here we have some of the cracks on these buildings, and also you have very long bridges. You cannot access these bridges. And also it is time consuming somebody has to go to the site and inspect and then report back what is happening. So we recently proposed a deep learning approach where, for example, we have an input image of 256 by 256 by 3, that is RGB image. We can divide those into different patches, and each patch is fed into a deep learning model where it can say whether there is a crack or not, and it can identify the locations where the crack are. Here is an example of this model being used for testing, that if you give an input and give this patch as above, then you can predict where the crack is. So this we did compare with 15 different CNN models listed here, and with an input size, and you can see there are like millions of parameters that needs to be tuned for this to work correctly, but it gives a very good results. So for example, here the top one is actually the ground truth and the bottom one is the predicted one. I think only in one case, if you see here in the red color, it has predicted, where in the blue one, it is not. So in some cases, we did a manual decision whether it should be considered as a crack or not crack. In some cases, most likely, most of the times it was giving very good result. So here is the performance. In terms of area under the curve, if you see, VGG model 16 gives around 98% AUC. That means it is almost 98% correct in terms of picking the right crack patch. Similarly, if we compare the inference time, because this is important, as we saw before, there are millions of parameters. If you give that to a system and if you want to do it in real time, it is very difficult. So if we see which model works better, here AlexNet gives the lowest inference time, but with a very good accuracy of 96% AUC. So one observation that we see is that, so if you use deeper CNN models, you have to be like careful about how you can use those models in real time, because often deeper models have more number of parameters. As a result, it will take longer time for you to predict something when you're using this model in your practical use case. So this is the fifth and final case study that I will discuss about stroke monitoring using a wearable watch. So if you look at our healthcare system, how it has evolved over time, classical health, if you see, you have a physician or a clinician who is checking the patient, monitoring for some symptoms. It will usually be in the hospital. And then comes the e-health, where the records of the medical information is all digitized and it is kept. Later came the mobile health, where the mobile phones evolved over time, and with the smartphone apps, you can regularly monitor your health status, also record some of the events, physical activities, everything. Next is the C health. It is a citywide health. What it means is whether you can integrate some other information such as pollution level, any allergic substances in the atmosphere, whether the temperature is cool on this road, etc. And next, the S health is kind of short for Samsung Health. It basically means that with wearable devices such as like watches or even like rings they use, you can monitor your physiological parameters such as blood pressure, body temperature, etc. They can sense all these things and integrate. Now, using these wearable devices, you can monitor somebody's critical physiological data, and you can seek help by alerting the health authorities as well as paramedics to send an ambulance if somebody is in the risk of being unhealthy or they need some critical care immediately. So for example, here, if a person wearing a health device had an emergency, the device can send alert through its network, and the ambulance can navigate to the person dynamically by adjusting the traffic lights. So everything is integrated now. So the ambulance requests that I need immediate route to this person, and the traffic lights are adjusted automatically so that the ambulance can quickly to that person to address the health need. So keeping that in context, now if we focus on stroke rehabilitation, this is one of the areas that where many people need long-term caring and also continuous monitoring. People in stroke, usually they would have difficulty in moving one side of the body, either upper half or lower half or both, and it will be severely affected sometimes. So this requires both the long-term monitoring as well as continuous monitoring. So the reason for this monitoring is because traditionally there used to be people monitoring a person, but it is not always possible to be present with the person, with the stroke survivor. We cannot always be there to monitor him 24/7 and address the needs. So instead, we need the technologies to increase the intensity of rehabilitation, as well as provide different types of exercises and monitor these exercises continuously. And we can get an update as to whether the person is doing the set of exercises that we have provided and whether that person is also doing it correctly or not. This will provide a good feedback to the physiotherapists as well as clinicians to understand the status of the person. So there are different ways of rehabilitation. Basically, we have robotic devices, brain-computer interfaces, stimulators, and wearable devices, virtual reality, and using also our tablet apps or personal computers. We'll just focus on wearable devices here in our work. So while monitoring the stroke patient, you need somebody to be there and address any challenges that they are facing, and also monitor how the person is recovering after the stroke. So for that, we need usually we need somebody to give a score as to how the person is improving, whether the person is improving or deteriorating. So there are two challenges. One is that requires somebody to be there for assessing the person. And the second one is, if we have two different person assessing, then there will be a variability in what the nurse 1 or nurse 2 gives against the doctor 1 or doctor 2. So there is some disagreement between the assessing options because of subjectivity. So what we see is that wearable watch, it can help us to overcome these challenges. And also it can provide continuous monitoring throughout the time period for that person. It could be like a week or a month or even more. So we have developed a system where we can collect data from upper limbs, that is from the hands. We tie a wearable watch and we collect the data such as accelerometer and gyroscope values, sensor readings, and we try to differentiate which arm is affected. So in general, the person will be staying in the hospital for 1 or 2 days. And during that time, we need to monitor the person. So using our system, we can capture the continuous information for 2 to 3 days. And we will be able to say exactly at what point the patient started improving or deteriorating after the person undergoes a surgery. So here is an example of how in our lab we developed this. So initially we had like wireless sensor networks, basically big. This was in 2012, and in 2014 we started using iPod Touch, and now in 2016 we have developed a wearable watch. So in all our application we use something called an NIHSS score. This is nothing but National Institute of Health stroke scale. It is a 5-point scale that doctors and nurses give, and when they are assessing, we would have these devices tied to the patient's arm, and when they will be asked to do a set of exercise arm movements, and then we measure their movement through accelerometer and gyroscope and map these readings to the stroke scale to automate the process of NIHSS scoring. So our basic vision for the whole of the stroke patient care would be something like this. So you have a wearable device with accelerometer and gyroscope and other sensors attached to the arm. And then you can collect the sensor data at hospital levels, as well as you can integrate data from multiple hospitals at a city or state level. And you can store the data or also do analysis using cloud computing. And the real-time algorithms that we have on the cloud, it can be used to alert healthcare workers, as well as send emergency services such as ambulance, as well as to the users, even for the patient, as well as the family members of the patient. So we can, here the machine learning algorithms mainly focus on identifying whether the patient is doing the right exercises, whether the status of the patient, it is motor recovery is deteriorating or improving, and also whether we can provide real-time alerts to physicians, physiotherapists, and users. So in summary, I briefly talked about these case studies: real-time urban forest monitoring, missing data imputation, crowd monitoring, crack detection, and stroke monitoring. So when we look at all these case studies, we can see that the overview of how all our system is working. In the sense, we have sensors, cameras, social media data, and mobile data, environmental data, and these are all heterogeneous data coming from different sensors and different types. And then we have video monitoring, structural health monitoring, environmental monitoring, health monitoring from apps or wearable devices, and transport. So everything, when you look at it, it is like different systems interacting, trying to interact together, and they are all coming together to a cloud or edge computing, and from where we try to sense, we try to make an approach of systems where we have some common picture, such as we want to have an intelligent system that can sense, connect, learn, and also act in real time. So I think the AI as a whole is venturing into this area, and it would be very interesting to see how the connected intelligence works in action. So some of the big challenges that I mentioned before, just recapping, is that how to understand the data is critical, ensuring availability of reliable data and validating the data, developing robust models, integrating insights into the system of systems for effective implement, and deriving knowledge and reasoning. So in essence, the way we see it as Internet of Things has ability to sense, connect, provide analytics and visualization by combining different sectors of our society, like transport, national infrastructure, factory, retail, entertainment, utilities, even personal users, office users, policymakers, everyone. It brings together by combining both physical infrastructure and digital infrastructure. And AI plays a vital role in seeing the data and making sense from the data and providing actionable knowledge as to how we can use the data and make decisions, and also react to the outcomes that the AI provides. I think that's all for today's talk. I would like to acknowledge the group members of ISNIP team at the University of Melbourne. And I'm happy to take any questions if you have.
Thank you, Aravinda, for a very great talk, and big data analytics and Internet of Things applications, various applications. Yeah, any questions from you? Please, if you have any questions, you can directly ask Aravinda, or you can just type in QA. Okay. So the first question, with pandemic crisis, do you think that the telehealth monitoring using wearables is trustworthy and sustainable in long term for healthcare management?
I think in my experience, there are now newer wearable devices where they are very precise, and the data that you get is reliable, yes, and also trustworthy. It depends, however, on what you would want to measure from the wearable device. For example, if you are trying to monitor blood oxygen saturation, it is called SpO2 in short. SpO2 provides how much oxygen levels you have in your blood. So usually it will be around 96 or 95% to 9900% for most people. So in case of pandemic, in the current pandemic crisis, if somebody is affected and is not able to breathe properly, then the oxygen level will drop may drop below 95%. And then from that, you could make out, okay, the person may be suffering from something. So it gives an indication. Yeah, so you can definitely use, but you should know like whether you can use the wearable device for what you want to measure.
Okay, thank you. And the second question, could you also elaborate a bit on the communication between cloud servers and the local computing devices?
Yeah, so local computing devices, in case of healthcare, if we look at it, so you have lots of data coming every second, maybe like 50 readings of samples. And you need to acquire them and process them, but you may not have enough time to provide like an intelligent level of decision at the local computing devices. So for that, it would be better you rely on cloud servers and also even edge computing with a little bit more capacity than local computing, but slightly lesser than cloud servers to do your processing or analyze the data using from different devices together. Local computing devices alone will not be sufficient. And also, if you develop an AI and you want to use at multiple sites, then it would be much easier to deploy them in the cloud. And there are something called REST API. Using them, you can actually get your prediction results very quickly, and it will scale. I mean, you need not like deploy your algorithm at 100 places. Yeah, keeping at one place, still you can be able to provide results at 100 different locations at the same time.
Is it kind of Amazon? Yes, you are using for that.
Yeah, no, we are using our own servers, and it is the REST API is like a technology, software technology that anybody can use. It is a kind of a service, web service that we can use.
Yep. And we have another question. Can you please share a short roadmap for how to go about AI in IoT, having some knowledge of IoT, steps to learning? So probably this question say that, for example, if some kind of shorter roadmap, and how, is there any data available in IoT as well? They can go with that one, because some data is real data, and many researchers, especially those they wanted to start IoT, probably they don't have access to those real-time data. Is there any artificial data in IoT? or any steps?
Yeah, I think one data set that I can recommend is there is something called UCI dataset, UCI data repository, if I remember correctly. So
Data. There are lots of data sets there.
there are a lot of data sets, and also there are a couple of data sets that they can obtain from City of Melbourne website. It is called Open Data. So they make the data set from the cities, make it available to the city people. They can develop apps and use them for anything that they want to use. And similarly, there is something called in most cities in the US and also in Australia. I think they are making many data from the cities as open. So I think it is usually called open data set or open gov, something like that.
Yeah. And also if you share any other short roadmap to how to start AI in IoT, regardless of the data, for example.
I
What are
would
the
say,
steps to learning?
yeah, I would say, I think it is an important question, and also it depends on what background somebody has. I would say that if you know how sensor devices work, like you are able to collect the data, and then you are in some sense one step is done. And the next step is when you are collecting the data itself, you need to know first what the problem is correctly, and whether you whatever the sensor that you put in and you try to collect, whether that sensor has any relevant information for your problem. And then you collect the data, and then you have to start doing this machine learning. And even in machine learning, the artificial intelligence, there are like unsupervised, supervised, semi-supervised clustering, different techniques. So I think it is a bit broad, but roughly speaking, I would say that first you have to know your problem very well, and when you're trying to collect the data, whether it makes sense to collect that data. And next, analyzing the data when it comes there. I think if it are totally unknown, then I would say better to contact some experts just to give an idea of how we can go. Or you can try some of the things what other people have done for similar data, just as a starting point.
Yeah. They're good points, actually. Yeah, as you mentioned, there are some open data as well in IoT, in UCI or in Melbourne City, or then the rest is some kind of machine learning and using some kind of algorithms there. Yeah, thank you. And any other questions? We don't have any other questions. Just one more question from me, very, very short. I'm just wondering how, especially for the health and stroke, how is the life's very important. And when you apply any machine learning, we have some kind of errors there. So is it possible to better for when you developing such algorithms, machine learning algorithms, just more focus on that class that makes problem. I mean, instead of saying that this is the stroke sign, for example, we need to call ambulance. Probably we can a bit change the problem, and we can give more warnings because it saves lives. And if we don't put this one in the algorithm, probably that what makes probably after some people they have a stroke, but our machine learning algorithms or our model can't detect those things. Do you have any of these type of issues in IoT?
Yeah, I think in many these health examples, it is not totally about how accurately you are detecting, but you are trying to get the sign whether that person has that. classifying or with accuracy is a different question. But when you are trying to find whether the person something is going to happen to a person and it is very immediate, those kind of things, it is mainly the sign that it is not with how much percentage of accuracy that you want to detect. It is whether there is some kind of that trend is there. Then okay, if there is a trend, you pick up, you give an alert. Because even if it is little bit off, then it is still okay. It is better to attend that person and treat, rather than, unless you're trying to aim for 100% accuracy. It may not be always possible because of every person has different nature and characteristics, and sensor readings what we get will be different.
Thank you so much, Aravinda, for great talk. And so this week we have another two also talks tomorrow and Thursday, and so we have also next week is the last week of our symposium. Hope to see you all there. Thank you so much all for participating and for your great questions as well. See you tomorrow in our next IEEE seminar. Thank you all. Have a good day.
Thank you. Thanks, Satar.
Thank you. Thank you, Aravinda.